All right, welcome everybody to today's Ascendo Reliability webinar. This is Fred Schenkelberg, and there are really two things, in my estimation, that as people concerned with reliability of the products or systems really need to focus on. And one of them is failure mechanisms, which we'll talk about today and illustrate to hopefully a good extent why we need to do that and how it's useful and interesting. And the other one is decisions. I know many of you have heard me say it before, but reliability occurs at the point of decision. And if we can provide the appropriate information to people making decisions that impact reliability, such that it influences that decision, that's a good thing. And a lot of what we do is we run a test and we create results and we provide that to somebody so they can incorporate that into their decision making. And that's just a quick sketch of it, but obviously going to be a subject of another webinar. But today I want to talk about failure mechanisms, and hopefully we don't experience any of them in the next 45 minutes or so, or hour, as it has happened a couple of times, but we'll see how it goes. All right, so failures. Now, some people think, a photographer's opportunity to take a look at a, rusted out, partially dismantled vehicle as a piece of art and a success in and of itself, and especially if they can sell it and make a living doing it. But the failures are defined broadly as the functions that we expect something to do no longer achieve those objectives. They don't function. This vehicle would probably not be suitable to run down to the store to pick up a quart of milk today. So we would probably classify this vehicle, if it was our primary mode of transportation, as failing to meet that requirement. Now, many of us deal with failures, but we also deal with the symptoms of failures. We see the lack of functionality, or we get an error message. I saw a quick note on LinkedIn the other day that somebody was sitting in front of their computer screen, a cartoon character, and there was crumpled up paper and all over the place. And it was like, finally, success. And I've got a new error message now. At least it's a different error message. And I know firsthand what that is something's not right, and you're troubleshooting, and you're just getting symptoms, and you don't really know what it is you need to go fix. So oftentimes when a customer says, hey, this isn't working, they describe symptoms. It doesn't power up. And I'm going to use that as a loose definition or an example of a failure mode. And that's not what I'm talking about today. What I really want to talk about is mechanisms. And if these images I got, so far, one of the most common ones is iron oxide is visible. Now, that may be the visible symptom of something going on, but it's also a chemical reaction that will degrade the metal's integrity. And so I'm going to call that a mechanism. Now, typically, being more in the physical world than in the software world, I call failure mechanisms are things that are the physical or chemical processes that change the material properties in an adverse way. That's not a complete definition of what a mechanism is by any means, and it's not always the cause, right? Sometimes the cause is, well, we didn't pick the right coating, or we didn't pick the right materials, or the right design, or for the environment, and so on. So there can be all kinds of different physical, chemical, or even software mechanisms at play that cause failures. And there's also a whole bunch of things that affect the decisions we make that lead us to create the particular product we're doing. And it could be the environment we're working in, the culture we're working in, the priorities that we're working in, the systems that are available, and so on. Not to minimize those, but today I'm going to really, really focus in on those how things fail from a physical or chemical way. And so I'm really trying to narrow it down a little bit, but I think the discussion works, and the focus, what I want to talk about, applies to pretty much the broader range of mechanisms that are out there. Now, I don't have a ton of experience troubleshooting software, so I don't really know how that works there, but hopefully the hardware side of the world will give us enough to chat about here. And there's certainly plenty of mechanisms out there. So as I alluded to just before we got started, what's your favorite mechanism? And I've been showing rust, basically iron oxides coming through this orange deterioration of iron. But what's your favorite mechanism? You can hit the chat window. Electromigration. You read my mind, Robert. That's one of my favorites by far. Fatigue, yeah. And that takes many, many different kinds of forms. Thanks, Bill. Resonance, natural frequencies. Yeah, that one can get exciting, Michael. There's no doubt about it. You know, I like the electromigration one because early on in my career, I saw a short little video, and this is way before YouTube's, and I even went looking for it. I didn't find that particular one, of a thin trace that then got over a huge amount of current pushed through it. And they used the time-lapse camera to capture the actual movement of the copper. And you could see it once it started necking down in one little region, that increases the current density, and the current then basically pushes the molecule, the atoms of copper in this metal off somewhere else. And then where the current density is a little less, think of it as a river, where the river widens out a little bit, it slows down, and then it started to build up there. It was a fascinating phenomena. Now, most of the time you don't get to see electromigration. But you do see the results. You have a open in one of your traces as it finally fails, or you may even get Kevin, a fan of Creep. It sounds appropriate for October here in the US as we're getting ready for Halloween. Yeah, but creep and contamination, fatigue, corrosion. Somebody lives in Florida. I heard that's a real problem in Hawaii also, where it's a hot and humid a lot. It really accelerates that mechanism, or range of different mechanisms. Now, each of these terms we're using, fatigue and contamination and creep, depending on the material you're using, the actual phenomena that's occurring may differ slightly, but the idea is that we describe these things in a similar way, as the material is slumping or moving in ways we don't want it to do. I don't know, did anybody mention diffusion? That's another one that I like, because it's kind of insidious. It can take apart things in a very slow fashion, but cause real problems. Right. So some quick examples, and you already mentioned a handful of those, and I just described electromigration. But these examples aren't meant to be educational. I'm not going to do big technical papers on these things. But the idea is that a good many of the mechanisms that we deal with in our products have names. And there's one or dozens, in some cases hundreds, of technical papers and conference papers, and in some cases whole books written about these mechanisms. And knowing what, so if you're working with an oh, now I'm drawing a blank of it, a capacitor. Oh, no, I'm drawing a blank on it. It's a can capacitor has a roll of foil in it, and it has a dielectric solution around it. Oh, what's the name of that capacitor? Electrolytic. Thank you, Bill. Thank you. Electrolytic capacitors have a phenomena where, by the nature of the way they work, they deposit this dielectric onto this foil that's inside the mechanism, inside the device. And that process of plating, basically, for lack of a better word, I'm sure there's a better technical word for what it's happening, the depositing of this dielectric on the foil and the removal of that in different circumstances creates a coating. And it's not always perfectly even. It's not always three atoms thick all the way across the surface, as a rough example. Now, the areas that are a little bit thinner have less resistance to higher voltage. And naturally, it's sort of like standing in line at the grocery store, that you go to the shortest line, but you know you're going to wait the longest because for whatever reason, at least that's been my experience. The idea is that because there's variations in that coating in this dielectric, the weakest spots are the ones that will see the voltage gradient in a different way than the ones that are thicker. And so it sees a concentration of that. In physical materials, say a beam, if the beam has a weak spot, say there is a defect or occlusion or a thinning or some material property that creates a small weakness in one particular area, it's very likely that the defect, the crack in a beam or the punch through or the lack of dielectric behavior within that capacitor will fail at those weak spots. And while there's many better, I should say, there are way better descriptions of what electromigration is or dielectric breakdown. What I find that reading all of these things and looking at if I'm dealing with electrolytic capacitors, and at some point we should stop and say, well, how can they fail? What is known about how this can fail? And doing a quick search these days, you'll find 5 or 6 different common ways these things can fail. And then if you really want to dive into it, go to the library and go dive deeper into the details. But even just being aware of them and knowing that if you apply too much voltage or a voltage spike hits a dielectric that has a weak spot in it, the likelihood of it failing goes up dramatically. So being aware of voltages across capacitors and the nature of how voltage is applied to that capacitor is a key thing to understand how to avoid that particular mechanism. I don't really know if solder joint fatigue is electrical or a mechanical. A lot of times electrical people have to, electrical engineers have to worry about it. Many of our component vendors and so on spend quite a bit of time designing appropriate solder joint designs so that they can avoid fatigue. We spend quite a bit of time with integrated circuit packaging to make sure that they are compatible with the substrates that we're putting them on so that we don't get undue amounts of forces and motion in those things that create fatigue. But one of the things that's fascinating about solder joint fatigue and fatigue in general is that it often includes that there's some kind of motion. Now, sometimes those motions are so small, you just really can't see it. And even it could be just changes in strain that it's actually experiencing, but it doesn't actually move, or it moves very, very subtly. And if you, like me, have taken a soda can or a pop can, depending on what part of the country you're in, and flexed it as an empty can, and you flex it a few times, sometimes it takes longer than others, and it depends on all kinds of other factors and thickness of the aluminum, for example, but it'll crack and break apart. Well, solder joint fatigue is very much like that, only on a much more subtle level. Now, years ago, I got a call from a company who was going to put some satellites in space, and they wanted to know if their solder joints would survive. And I says, well, what conditions do you expect these solder joints to see? And they said, well, on the dark side of the orbit, there'll be, minus 100 degrees or some amazingly cold temperature. And on the bright side of the orbit, they're going to see, plus 100 degrees or some other amazingly hot environment. And that's bigger than most of our acceleration chambers that we use to test these things. So once you put up a bunch of test samples and see which ones work, because you get results in orbit much faster than you would in the lab. We often have a hard time even achieving those ranges. But these are just a couple of electrical ones. And within diffusion, within corrosion, within solder joint fatigue, depending on what solder you're using, the fundamental mechanisms, the chemistry and physics that's going on, vary. And sometimes the dwell time matters. Sometimes it really doesn't. Sometimes the elasticity range matters. Sometimes it doesn't. And on and on and on. So that's just a couple in electrical. In mechanical, a handful of you mentioned these already, is wear and fatigue. But there's just corrosion in and of itself. The images I have are mostly of rusty vehicles today, but that's one kind of corrosion. One of my favorites was, I was helping a friend last weekend on a project, and he had a plumbing project, and he had a pipe he needed to attach an extension to or something like that. And he was ready to put this, I want to say aluminum, but it was probably galvanic coated something, to a copper pipe. And he says, you know, you might want to think about that. And the reason is that there's this galvanic corrosion, where if you have dissimilar materials and there's dissimilar metals, enough of it, and there's even tables to show you which are the worst ones to put together. And I don't know the details of galvanic corrosion enough to have explained to him why that's a problem. But I said, you know, we need to check this. There's probably a coupling that will allow you to isolate these dissimilar metals and avoid the chance of corrosion. And I did a quick search, and he said, yeah, you're right. All right. So you needed a different part. But just being aware of the range of different mechanisms that are out there. And some of that comes from experience, because you run into it in field failures and details that occur within your products. But if you work proactively and spend the time to think through, like an FMEA to a large extent, well, how could this fail? What's known about this? So what about in plumbing attaching dissimilar metals? Or what do I need to be aware of in connecting piping systems? And there will be there's more than one website that will list all kinds of cool things, and usually with great imagery that say, well, here's things to be aware of. And then, of course, like I said earlier, is you can dive into it and learn a lot more. Now, in manufacturing, as you know, many of you know, I started in the manufacturing as a supervisor and then as a manufacturing engineer in my career. Is manufacturing can only make your product worse. It really can't make it better than its initial design, unless you start changing the design. But the idea is that we make mistakes in manufacturing, and I include myself in that group. Is we sometimes apply the wrong parts or in the wrong orientation, or we damage the parts as we go along. And many times, the types of defects and issues that come in, whether from the vendors or from transportation or handling of the parts or the assembly of the parts, can be latent defects. We create a small crack, say in a multi-layer ceramic capacitor. Our electrical testing looks for capacitors to appear like an open. And if there's a crack in them, 9 times out of 10, that appears like an open. So we think they're okay. Now, you can detect the cracks using all kinds of different techniques, but they're usually very expensive, and it's much more prudent to just get your assembly process in working order and make it stable so you don't damage parts. But they still occur. And the idea is that crack, this latent defect that we have in there, it might be the cause is because we flexed that capacitor or hit it too hard, or it got hit against the support or part of the assembly equipment, or it could have been a thermal gradient across that it was too high and caused that that essentially piece of glass, these ceramic capacitors, to create a small crack. And then you add thermal cycling to it. And in normal use, you heat it up and cool it off in, say, a diurnal use conditions, or it's in a solar array. So it goes to ambient temperature overnight, but then it heats up as it's being used and it's in the sun through the day. That kind of thermal cycling then takes that crack and propagates it. Now, what's the real mechanism there, right? Is it that we have a physical overstress that caused, or a temperature overstress that caused a crack? Is that the fundamental mechanism? Or is that one in a string of mechanisms? Because if that same part with a small crack goes into a thermally stable environment and stays in a very tight range of temperatures, that crack might not propagate for years and years, if ever. But in a high thermal environment, that small bit of damage then can lead to problems. And that's just one example of the complexities of many of these mechanisms that we have. They may string together. They may be, one of my favorites is popcorning. And I'm sure there's a better technical word for it, but it's you take an electronic component, say like an IC that has the epoxy overcoating on it. And if it's a little bit too much moisture inside the package, and you run it through the reflow oven, which exerts a lot of heat to it in a very short amount of time, it eventually, it has the potential to change that moisture to steam, and that greatly expands its volume, and it wants to release that pressure somehow. And oftentimes that creates a crack or an opening to the outside of what should be a pretty tight seal around that device. Now, the hard part about that mechanism of popcorning, it's like that crack, it just creates the opportunity for failure later. It disrupts the thermal dissipation of that IC. It allows an ingress for contaminants to create corrosion problems, and it can create a number of other issues like breaking wire bonds, which would be even more immediate. But that's where many of our mechanisms may have 2 or 3 or more steps for them to occur. And those are often the most fascinating to me, is that when there's an initiating event that creates the opportunity for another mechanism to take over or to be accelerated or come to fore in a much quicker way. So how many ways can something fail? I've only touched on a dozen. And I think for any component, you could come up with a dozen. Bert, I was going to tell that story about the cracking a capacitor from depaneling, because I actually saw that in a factory one time. They had hired a brand new person. They put them on the end of the line where they're taking these circuit boards apart from a big panel into their individual boards. And they said, well, you bend the tabs off. And so he would grab the circuit board by the electrolytic capacitors, which turned out to be a nice handle, and then just bent the entire thing. So the entire board would bend. And you could hear stuff on that board, probably the electrolytic capacitor or the ceramic capacitors cracking. But I think there was also vias cracking and traces cracking and all kinds of other problems. The proper technique was to lay it flat on a table and support it and bend only the scrap away from the board so that the board didn't see any flexure. Nobody told him that. He was like, oh, I got to take these apart. I'll take them apart, and just started snapping away. Well, most of that batch we took down to the lab and looked for cracks, and all of them were scrap. There was no way we're going to fix those things. There are so many ways things can fail. It keeps us in business. There's no doubt about it. And as soon as we create a new material, we create a dozen new ways it can fail. For me, it's job security. All right. Now, one of the things that we need to do, besides thinking through proactively, well, how could this fail, and do the literature search, is especially when you run into, well, this is a new material, or this is a new design, or this is a novel new way to apply this set of materials in this circumstance to create this new solution. Well, part of it is then saying, well, what's the advantage? What are we trading off? If we make this beam thinner, it's going to be lighter, but are we still keeping the same loads? Now, how can we make that difference? Well, we change the manufacturing process or the grain structure and blah, blah, blah. And they go into detail about this. And you're like, all right, great. Well, what happens if that grain structure is not quite perfect? Maybe it's just variability. Now, sometimes reliability folks get a real bad rap because we walk into the room and talk about all the ways that something could fail, and we're interested in only how it won't work. And most everybody else wants to figure out something that will work. But part of it is being just curious. Well, how is it supposed to work, and what happens if it doesn't? What's the consequence of these failures if they occur? Now, what could cause that to happen? And we start asking 5 whys, or thinking through it in a brainstorm session or whatever, is how can it fail? Now, part of this is important because as we start using this material and building prototypes and evaluating it this way and the other, do we want to apply high temperature to it? Is that relevant for the mechanisms that are at play? Does this material have a diffusion possibility that changes the material structure such that it's weaker? And well, we need to be able to monitor that or measure it, and maybe temperature is the way to accelerate that diffusion. But if we didn't think through that diffusion could be a problem, and we didn't have any other thermally excited mechanisms on our charter, we probably wouldn't see it. So part of it is are we applying the correct stresses for the suspected mechanisms that are there? And then 2, are we measuring the things that would detect phenomena that we need to be aware of? And part of that is this being curious, and being available to look for what could go wrong. And yeah, sometimes it's annoying. You got to be careful with it with the folks you're working with, especially the person that's designing it. But ask them, what are the trade-offs? What are the weaknesses areas? What are the areas we don't know enough information about to be solid that this is going to work? What are the elements that we need to be cautious about and learn more information so we can make good decisions? Another way we learn about mechanisms is, well, hang out in a good failure analysis lab. That's just fascinating. Back when I was at HP, we used to do it was once or twice a year, we would get the folks at the FA lab to do a webinar, and they would be just, here's the top 10 things we're seeing in the last year. And they would always have a story and pictures behind it and all kinds of cool stuff. I learned a ton about all kinds of ways things could fail that I had never, ever heard of before. So, and I know there's a handful of folks on LinkedIn that provide how metals fail and what you can read from metals. And there's other companies that have root cause analysis techniques and processes and procedures. But the basic idea in root cause analysis is to really get to that understanding of what's happening on a physical or chemical process. You're the detective. This is our CSI moment, is ask enough questions and get enough understanding that you know that this is occurring because of this chemical reaction, in that it has to have these 3 reactants and a bit of voltage, and temperature doesn't matter, or vice versa, or whatever the particular mechanism is. Can you turn it on and off? Do you understand it well enough that you can actually recommend changes to the design or the material set or whatever we're using that is involved in this process that leads to failure? Can we interrupt it, for example? You know why fans are in computers? It's to cool it, right? Well, why do we want to cool it? Well, temperature in electronics often leads to diffusion and creep and migration, and it speeds up corrosion and dozens of other processes, many of them chemical, that can cause equipment to fail. Plus, putting your laptop on your lap when it's a bit too hot to touch is not pleasant. But the idea is that temperature is a pretty good stressor for many, many different kind of mechanisms. Not all, and it's not generic, and it's not something to be used in all cases, but those are stresses. That's not the root cause. It's an agent or a stress that acts on causing the mechanisms to fail. So please keep that in mind as you go through the root cause analysis. But the underlying cause isn't that it got too hot. it's that then it melted. The melting is the mechanism. And so if you can avoid it getting too hot, then you can avoid the melting. Kind of the logic that simplistic logic that I use. The other one is just pay attention. Look for things that are just not looking right. Now, the images I have of these old vehicles, it's sometimes if you're looking for a used car, you would probably know that these are mostly fix-up specials or really just piles of scrap. If you want to melt it down and create your own vehicle, you could drive forward with that. No pun intended. The other way to go about doing this is just be aware of what's out there. And part of it is, as I mentioned earlier, is think through, well, how could this fail? What have other people seen with these failures? And usually one or two searches or a trip to the library will give you a wealth of information to make you wonder why it would ever work. But the idea is to create an ongoing regular routine of learning about mechanisms, and especially with the ones that are related to your product. Now, a couple months ago, I got an email, a question that said, is there a good resource for what are all the mechanisms? What are all the failure mechanisms? I wish I knew. I know that in the polymer world, there's tons of papers about how different polymers, each different grade of polymer reacts to different stresses. And it's usually focused on how they perform. This one has particular strength properties, or this has particular tensile strength properties, or this one has basic insulating properties or coating properties. And the papers are focused on how well they perform their function under particular circumstances. And oftentimes those papers include where those boundaries are. So if I apply heat to this, or if I change the application process, or if I do cycling, then these kinds of mechanisms will appear. And so the mechanisms are buried underneath papers talking about the performance of those materials. In metals, they often talk about, well, how much load can it take, or shear can it take, or torsional loads can it take before it fails? And they talk about grain structures and assembly processes and cooling rates and all kinds of cool stuff, and how those metals are manufactured. But again, they often judge those material properties based on how well it does against particular types of failures. And then they usually examine the underlying mechanisms that go into it. I know in the reliability world and in physics of failure world, we often focus right in on the mechanism. And so for those electrolytic capacitors, dielectric breakdown often then includes, well, what kind of dielectric you're using, what kind of voltages are applied, what kind of sequencing of voltages are there, what kind of spike suppression is involved, how thick the dielectrics and the foils and the spacing, all kinds of weird details go into creating a model for what's the likelihood of dielectric breakdown. Now, those guys tend to focus on, well, what's the mechanism? So if I have a particular type of corrosion, there's probably a model out there that says, well, if you've got dissimilar metals on this broad range that are very likely to cause this galvanic corrosion, then this is how fast it'll go. If you've got metals that are insulated from each other and are very similar, not dissimilar, then the possibility or the rate of galvanic corrosion will be very minor and very slow. Some mechanisms are very well understood. Unfortunately, about the time we got tin lead solder very well characterized, and after using it for 50 to 75 years, Europe decided that lead was bad, which I wholeheartedly agree with, and we don't want it around, especially in our landfills and water tables, that we ended up with all these new materials and new types of solders that we had to start over again. And while they had similar mechanisms, they were subtly different. And so what we learned about accelerating tin lead solder joints almost applied to the new ones. And industry-wide, there was a lot of research on figuring out the new mechanisms. But a third way to go about keeping up with mechanisms and learning about mechanisms is build your network. Going to a conference or attending a session or going to a class or just with the people you work with, look for those folks that have deep knowledge in the areas that are relevant for what you're working on. But also be aware of the folks that, you might not need to know a polymer scientist right now, but maybe 2-3 years from now, your company is going to start using this novel new polymer in their applications. And having somebody you can tap into and say, Sarah, how does this where do I find more information about this polymer and how it works and doesn't work, can be incredibly valuable as you start to explore and get to know how different new things into your world can work or not work. I had a failure analysis, and I know I talked about this story a number of times. I had white powder on a circuit board, which is generally a sign of corrosion. And one of the clues as to why we're getting this particular kind of corrosion is to do a chemical analysis of it and figure out what is in that corrosion elements so that we could backtrace where the contaminant came from. Because usually on circuit boards, there's some kind of contaminant involved that either gets dropped on or touched on or placed on or somehow introduced to a circuit board that creates this white powder type corrosion. And what came back to me was that it was this material called squalene was the predominant element in this material, this stray material found on the board. And it turns out squalene is inert. So it's like, how's that going to lead to failures? And then I went over and talked to one of our material scientists that knew all kinds of different chemical type stuff and asked her about it. And she said, oh, squalene is natural. It's in your fingertips. It's a natural occurring material. So you're probably looking at somebody that put their fingers on the board and maybe he was using a lotion that contains a lot of squalene in it. And I'm like, oh, okay. So we went back to talking to the folks at the factory and was looking at board handling procedures. And because your hand, not only having this inert material on it called squalene, which is kind of the lubrication that you can feel on your hands. I'm sitting here rubbing my thumb because you can feel it. It also has ions on it, chlorines and bromines and other ions that are initiators of corrosion that on a circuit board wreak havoc. So even though squalene was the number one thing there, it was a clue knowing that one of the mechanisms that we get is corrosion that is usually caused by these ions that occur that get introduced to a board. And air pollution is another good source for ionic contamination. But having a stable of people that have deep knowledge in various different areas and different experiences is a great way to just stay in touch and say, hey, do you ever see this thing before? What's this squalene stuff? Where's that come from? You never know when you have an odd question and you might have 4 or 5 people that really know the answer. And that's very enjoyable. Yeah. Robert's got a note here about FA labs. I don't see it so much from the FA labs, except from vendors, is that electric overstress. Now, one of the things, ESD is a source for electrical overstress. It's a common technique for applying a very high but short spike of voltage to something. But electrical overstress and ESD damage, in many, many cases, especially with ICs, is very hard to detect, to actually measure it or to see it, and it's usually because you can't see anything else obvious. The likely thing is electrical overstress. And so without evidence, and even sometimes without samples, I sent a set of samples back to a vendor once and said, it's on the way, here's the tracking number. And they said, oh, it's overstress. Even before it left my building, they they said it was overstress. So their credibility in their research of doing failure analysis took a big hit at that moment. Vendors love it because it's very hard to prove. It does occur. There's no doubt about it. And it could be the design, it could be the board handling, it could be all kinds of different circumstances that create it to occur. Now, Dick Moss, years and years ago, he said, well, there's typically 5, and I was frustrated with some vendors I was trying to get some good information from. And he said, first off, don't send it to the vendors. You know, there's a handful that do a really good job, but send it to, we have a lab inside HP, send it to them. They are on our side. And if you're in a company that can't afford a big capital investment into your own failure analysis lab, set up a partnership with a FA lab in your area and let them do the research for you. Then send the results to the vendor to say, here's the evidence that here's the issue we need to solve. You give them some information to help them shortcut them from having to tell you that it's, well, we think it's electrical overstress. But Dick said that there's really 5 standard answers you get from vendors. We've never seen that before. It must be something you're doing. Or we know about that and we've already fixed it. To electrical overstress, or ESD, which is nearly impossible to actually prove one way or the other. It can be done, but it's usually by luck. That's not possible. I've heard that one before. We've shipped millions of these and nobody's ever told us about this. You must be making that up. I had one vendor, we did a joint testing of their system and 29 of the 30 samples failed. And they said, well, this is the 5th greatest reason I get from vendors. Well, that was just a random sample and you ended up with 29 out of 30 that failed for this particular mechanism. But in the field, we shipped 10 million of these things and we've only had 35 total failures ever, counting your 29. And so I did a quick hypergeometric calculation and figured out it was the random chance of getting 29 out of the 35 that they've ever experienced out of the 10 million they shipped was something like 10 to the 59th or some ridiculously high exponent. And I concluded the paper saying, I think this is highly unlikely. And my boss was upset I didn't use impossible. But it's not impossible. It was very unlikely. And they backed down from their claim that it was just due to random chance of picking the wrong samples. Now, sometimes vendors do a really, really good job and can really be insightful and helpful if there's something in it for them, right? It's not just more business. Sometimes it's working with our folks for the symptoms and the importance of it and what we're observing to help them understand how to do the failure analysis. And then maybe it's process control. I've done that with a couple of teams, was you help them improve the stability of their process, because on a routine basis, this one group was having batch problems. The whole day's production would go bad. And it was in their best interest to not have all that scrap and all these complaints. And it turned out to be process control. They had a variable process. And when the weekend shift came in, they did things differently and caused problems with the variability of the product. And that was enough variability that they had way more failures in the field. So there's all kinds of things we can do to learn about failure mechanisms. One of them is just experience, seeing these things and taking the opportunity to learn. But more importantly is use all of the resources as much as you possibly can, one, to learn quickly, but also to be aware of what's out there. What are all the possibilities out there? Now, is there a good reference? I don't know. I mean, there's physics of failure listings, and there's various textbooks that list different things. There's my favorites by far, being sarcastic here, is the ones that list the failure mechanisms that have different activation energies, and it's useful for using the Arrhenius equation for acceleration or modeling. But the activation energies for some particular mechanism might range from 0.2 to 0.6. And if you put both those numbers in and run the calculations out, you get wildly different results. So yeah, it's nice to know that this mechanism has a range of activation energies, but which one is useful for me? Which one relates to my materials? And that takes some more work. You can't just assume an activation energy. I think that's just criminal. But using good technical information and understanding of your particular circumstance and how that activation energy applies to your particular chemical reaction, then you're off to into a good place. But there are technical papers, conference papers. I just saw an ad for ECTC, Electrical Component Technical Conference. It's their 75th year. Those papers, that conference often gets into way too much detail about mechanisms for different components and new novel ways of construction and so on. I know I've gone through many of their proceedings over the years to find information. It's just one of many, but it does take some work. It's going to the library with a vague card catalog of where to go. So I've just made it a habit since early in my career to scan all those things, to look into them. And some things catch my attention just because I didn't know that could fail that way. And I learned a little bit about it. And others are, oh, I think I saw that last week. Let me dive into that and learn a lot more. But being aware of the broad range of mechanisms that are out there are great. But I don't know of the Oxford English Dictionary of failure mechanisms that gives us enough details to know what's what. There might be some out there, but if you know of any of them, let me know. I'd be happy to share that with the rest of our community. But usually it takes some work and some digging to learn about what's out there and what's available to cause failures for us. Now, having said all this stuff about mechanisms and why we should learn about them, and there's gazillions of them out there, the reason is that, and I go back to Henry Petroski, and I'm trying to, I think he was, I want to say Duke or North Carolina, in that region of the world in some university role. But he studied the history of design work and designing and creating products and all those kinds of things. He's got a bunch of different books out. But one of my favorite parts was design paradigms. And one of the opening parts, and I think it was in the introduction or first chapter of design paradigms, was this concept that designers inherently design away from failures. And the premise was they want to make something that works. Now, vast majority of designers I've ever worked with or met, I would concur with my observations that they want to make something that works. Now, they also want to make something that works and get it out on time and on budget and all these other factors. And they wish they had more time and more budget, but they don't. But they want to make something that works. And one of the factors of that is they need to know, well, how can it fail? And oftentimes designers start off by saying, well, I'm going to put this together, and if the green light doesn't come on, which is a failure mode, then they know it's not working. Now, the more information they have about how that electronic circuit has failure mechanisms, like if you don't connect these wires up correctly, that they don't carry the voltage into the places that would ignite the filament of this light. The basics are they learn in school. Petroski, Petroski, I believe. Charles, I think that's how it is. But if you look for design paradigms, that's a book that I know is unique to him. And he's got a handful of other books on it. Amazon is probably your best search engine for him. Somebody else may be able to catch the spelling for me. But the idea is that designers tend to design away from failures. And so the more they understand about the potential failure mechanisms if the material set they're using, the components they're using and so on, the better. For example, an electrical engineer that doesn't know that placing a ceramic capacitor next to a screw hole that is used to hold the circuit board down dramatically increases the chance that that board will deflect underneath that capacitor and crack it. It doesn't take much. If you over torque that screw, it'll deflect that board and you can crack things that are nearby. So one of the things we would impose on electrical engineers is keep out ranges. So we know that this circuit board deflects when you put a screw into it to hold it to the rest of the system. So we're going to make you stay, 5 millimeters or 10 millimeters away from that. And you get some pushback every now and then. Hey, I need the area of this board to complete this layout and create the circuit. And he says, well, here's the risk you're taking. And it's not just an arbitrary keep out region, it's to minimize and design out the possibility of this mechanism of this board deflection causing a crack in a capacitor. And so some of them we create guidelines, we create education, we influence the design team so that they are aware of the mechanisms at play. Many of them are already very familiar with lots of mechanisms, and I've learned tons from all kinds of engineers as they design. But part of it is also that we need to make sure it's stable. So if there's a design spin or a change to improve some function of this product or some defect that we find in the field and then they spin the board again, did we just violate all those keep outs and now created a whole new raft of potential failures? So parts of the processes in our design and manufacturing is being aware of what could fail so we could proactively avoid or mitigate those. Like if we know that this polymer we're choosing is going to melt under normal conditions, well, let's not use that. Let's use something else that has a higher melting point or softening point. Sometimes it's a trade-off with cost. Sometimes it's a trade-off with space or weight or whatever it happens to be. But whatever those things are, is we usually have options if we're familiar with the risks involved with the mechanisms that are coming along with the material set and component set that we're using. But it involves being aware of what could fail, is knowing what all these various types of mechanisms are and being able to articulate it and say, well, here's the risk, here's the options. And sometimes you need to dive pretty deep to really understand the phenomena that causes it. And so that you can accurately articulate what's the risk involved. How bad is temperature for this particular circumstance in our application? And what's the rate of failure if that occurs? Well, what happens if they use a higher temperature environment or it gets used in a higher temperature environment? Well, then there's problems. So it's one way to influence the designs is helping folks understand where the highest risks of failures may occur. And the sooner you do that, the easier it is to alter the design, obviously. So all kinds of good info there. Another is when we do accelerated life testing. I had a question last week. Somebody said, we want to do an ongoing reliability test. So we're going to use a handful of stresses to replicate and accelerate the use conditions. And I have no idea what product it was or what their acceleration models were. And I said, so if this is on a whole system, what specific mechanisms are you trying to accelerate? And even in a simple accelerated life test and using just one mechanism, you really need to understand that mechanism and how it works and doesn't work and where the phase changes are. So if you're doing something that involves water, are you safe going to -40 and plus 120? Because you're going to cross a couple of thresholds there with this material phase changes. And does it still behave? And with water, it's almost certainly doesn't. The same as when it's in liquid state. And this is just a tip of the iceberg of all of the caveats and concerns and assumptions that need to be validated. But the number one thing I see people doing with accelerated life testing is they say, oh, we'll just put it in the chamber. We'll put the whole thing in the chamber. We'll assume an activation energy for Arrhenius of 0.7, and then say our product is good after so many hours. I really, you've got polymers in there, you've got chemicals in there, you've got mechanical structures in there, you've got things that really need thermal cycling for them to even be accelerated at all, and you're using a standard temperature. You have things that need I have people don't power the system. They put it in the chamber and apply heat to it and say that's good. There's a whole raft, a whole family of failure mechanisms that require voltage gradients and current for them to even occur. Others take contamination. You know, they have to be exposed to dust and debris and air pollution. And then the failure mechanisms that are going to really take you apart in the field start to occur. Anytime you're accelerating, we're taking a gamble that we've got a experiment that will give us meaningful information under use conditions. And the less you think that through, the higher risk is that you're just going to have problems interpreting and understanding those failures at the end of the day. And you can run a test and you think you got a great answer, but it may be very, very useful. And in my estimation, is because you really understand the acceleration factors and models for specific mechanisms that your stresses actively interact with in a meaningful way. If you don't, you get a random number out, as far as I'm concerned, and it makes it very difficult to design and test for a whole system unless you really understand the mechanisms at play. And even with a particular material, you really need to understand the mechanisms in order to design and build and understand a decent accelerated life test. Now, there's obviously way more to ALT, but the number one thing I see, and I just saw it last week, was this, well, we just want to accelerate stuff. All right, well, stuff, something that you understand. He says, no, we just want to replicate its use life. That's great. But we can't possibly in the lab replicate 20 years of actual use conditions for every mechanism that could take apart your product. So be careful with that. It's kind of my take on that whole process. And then modeling, physics of failure modeling, and all kinds of other modeling we do can rely on just the mechanisms. One of my favorite examples was the inkjet printer nozzles, the little device that actually spits the ink. Last time I talked to these guys at a conference, they had identified, I think, 29 or 30 distinct mechanisms, ways their product can fail. And they model those mechanisms similar to a physics of failure as best they can. And then they use Monte Carlo tools to say, well, we're going to have these different use environments and use conditions and printing speeds and all these other components of stresses that would impact one or more of those 30 or so failure mechanisms. And then they would run that model and they say, all right, here's how long we expect this model or this design to last. And they've been doing it for years, but they early on focused on failure mechanisms, not design components, not material sets, anything else, but do we have ink shorts? Do we have corrosion? Do we have migration? Do we have cavitation? All these different phenomena that they can understand in great detail and model it. And it becomes a great tool for them, one, to estimate how well their product is doing or their design is doing. How well does it mitigate or minimize particular failure mechanisms? It could be used to trade off different mechanisms for particular environments and so on. It gives them an amazing amount of information, but it took the investment, like a physics of failure model level investment, to characterize the failure mechanisms that were present in their products. Now, some products, like a vehicle, there's 10,000 individual components kind of assembled on a set of wheels. There's lots of ways that can fail. So sometimes it takes prioritizing. Let's look just at transmissions or some other element of it. But the idea is that we use failure mechanism information in our designs, in our process assembly, and the designs of our products and our assembly systems, and to some extent our supply chains, but we also use it for accelerated testing or ongoing reliability testing or all kinds of things where we're invoking some kind of acceleration to some extent. But we also use it for modeling, or we can, and it can use it to great effect in each of these cases, if and only if we understand the failure mechanisms. And so that's a short set on why I think understanding mechanisms and focusing on failure mechanisms is really, really important. And there are bound to be other ways we can use this knowledge. Maybe it's even to do a webinar on occasion. What I really need to do is find a good failure analysis lab that wants to do some webinars with great pictures and stuff. Although I suspect non-disclosure agreements would probably thwart that effort. When I did it inside HP, we didn't have to worry about that too much, and it was amazingly useful. So that wraps up the one I got today. And thanks, Kevin, for the proper spelling of Henry Petroski. I was actually pretty close. I might have skipped the R. But the book, and it's been around for a while. Design Paradigms is what has been pivotal in my understanding of how to work with designers. It's been very, very useful. So I highly recommend it. And I saw Bill Meeker is on the line, and I just got a couple of copies of your books that were recently out, and it's out of reach right now. But you got a second edition of the one about statistical analysis. Bill, what was the name of the other book that I thought was going to be similar to one I'm working on? If you're still on the line. Yeah, it's downstairs, so I can't even see the title from here. But that's another author right up there with Henry Petroski. I highly recommend, and Bill and a couple other co-authors have come out with a couple new books in the last couple months, and those are obviously highly recommended. Let's see. And just as I was getting set up today, I noticed a failure mode with my system here. Thanks, Bill. Achieving Product Reliability. It's a fun read. I highly recommend it. And it'll help you improve. I like it because it'll help you work with your design teams in a meaningful way and help them get the information they need to design reliable products. And as expected with Bill, there's going to be some statistics in there, but it didn't seem to be too terribly heavy on that as opposed to some of your other works, Bill. But it was I thought, very practical. So I highly recommend it. Trying to think of what I just had on the tip of my tongue, another book that I'd highly recommend. But the one that comes to mind is by, has nothing to do with reliability or statistics, but it's on presenting information. And well, I've recommended it a number of times, and now I've drawn a complete blank. So any other thoughts? We're right up against the last of the hour here, and I appreciate everybody showing up today and participating. I'll hang out on the line here if there's any other additional questions or comments. If you have any ideas for future webinars, let me know. I'm always looking for good ideas, especially from the audience and for the folks that care to participate. I should have the recording up in a day or so, along with the slide deck, and we'll see how that goes. Let's see, I think I have one more slide there. There we go.